So, hello everyone, let's solve Mext exam, physics question 2009, undergraduate students, question 1.2, okay. So, what is the question? So, what multiple of the distance between the center of the earth and that of the moon is, so this first part is the distance between the earth to the moon and the distance between the Earth and a geostationary satellite. So, first of all, let's say, 1 second, if you have here the Earth, okay, so let's make it a bit big. So, here maybe the orbital of the moon, okay, so this is the orbital of the moon, and this is the distance of the moon, okay, and here we have the orbital of a satellite. Now, here comes a first part of the question, okay? It might be obvious for some people and not for others. So, a geostationary satellite, okay? What is the period of a geostationary satellite? The question wanted you to know this, okay? So, a geostationary satellite has a period of 1 day. So, for those who don't know, what is a geostationary satellite? It's like he keeps pointing to the same point, so the earth is rotating around itself, right? And this satellite is always it's always in the same point. So like if you live here and the satellite is here, the earth rotate, but the satellite keeps pointing at you after it rotates, so that you have signal, maybe internet or I don't know what, but it keeps on in here. Why do you need to use this? You will see, because here he finished the question saying you which always stays above a fixed location of the equator. So it makes it easier, so that here you know it the distance is to the center, and take this the cycle of revolution of the moon around the earth to be 27 days. So here he tells it both the periods, of the satellite and of the moon. Okay, the moon is 27 days to make a whole cycle, and the satellite 1 day. So he wants uh, the this is the distance to the moon, and here the distance of the satellite, and he wants what multiple of the distance from the center of the earth to the moon. So let's say this multiple over here is x, multiplied by the distance from the earth to the moon, so let's call it dm, is equal to the distance from the earth to the satellite. Okay, so let's call it ds. So ds is the distance from the earth to the satellite. Okay, so how do you solve questions like this? So the moment he tells you about periods, what you need to remember are few formulas. 1 second. If he gives you like a string and a mass, anything like many strings and anything like this, the formula is 2 pi and here m divided by k, right? For a pendulum, it is 2 pi square root of L divided by G. Okay, if you don't know these formulas, don't worry, it might help you for other questions, and then you study this subject. But for this, when he gives you forces and circular motion, what you need to know is that in a circular motion, what you have is a centripetal force. A centripetal force which is given by mv squared divided by r, and you can write as v is equal to wr, which w is the angular velocity. So w gives you the velocity it takes for the rotation velocity, right? The angular velocity. So if 2 pi is for you to make a whole loop, a full cycle, divided by t, big T, which is the period for you to make the whole period, which is the period for you to make the full cycle. Okay, so so this is the relation you will use to get to the period. Okay, so the centripetal force is equal to m, but v squared, we can use this relationship over here, which is v is equal to wr. Okay, so wr, or big R, it is the same, which is the distance between the rotation it's like the hand where it's spinning. So squared divided by R, right? So what you'll get over here is, let me put this relation over here, V is equal to WR. So we will get a formula over here. The centripetal force is equal to mw squared multiplied by R. Okay, and this is the formula we are going to use with this part over here. Okay, now what we need to know also is what's making this centripetal force, what's making it rotate is the centripetal force, but what is acting on, like causing this centripetal force over here? When you have a planet and like the moon rotating, what force is acting? It's the gravitational force, right? Which is given with G, big M, the mass of the Earth. Here it is the mass of the moon, divided by, now here it is the distance, right? Which distance? The distance to the moon squared. Okay, this is equal to what? To our centripetal force, which is given with m w squared multiplied by r. R in our case is the distance to the moon. Distance to the moon. Okay, so here we'll have this cuts, so we'll have that w squared is equal to gm divided by d, the distance to the moon, cubed, right? Because this goes to the other side, cubed. Okay, but what was w? W was 2 pi divided by t. Okay, so 2 pi divided by t equals this square root over here, gm divided by d of the moon cubed. Okay, so t, the period of the moon, which he already gave us, it is 27. Okay, 27 days. It's equal to 2 pi, the square root of the distance to the moon from the center of the earth cubed divided by gm. Okay, so this will give us the period of the moon. Now he already gave us this. Now a fun fact, like if you wanted to know the distance to the moon, you can find it over here. How's that? Like g is a constant, m is the mass of the earth, these are constant, and here is 27. Okay, so if you wanted to find the distance to the moon, you can find it, but we don't need to, because what is this t over here? It is 27 days. So let's save this equation over here. Okay, we will. So what do you think we will get when we are trying to find this equation for our satellite? Try doing it by yourself, because it's the same thing. Okay, what we will get is that the period of our satellite will be 2 pi. I will do it. I will deduce the formula again just so that we can practice. Okay, but try to do it by yourself. D to the satellite cubed divided by gm. Notice that it doesn't depend on the mass of the satellite, neither does over here depends of the mass of the moon. Okay, the mass of the moon over here cuts. Okay, so let's find to the satellite. It's the same procedures. Really try to do it by yourself, even to gain time. Okay, so let's say now over here we have the earth and now the moon, not the moon, now the satellite. Okay, so this is the distance, this is ds. Okay, so what force is applied? The gravitational force. Okay, g, the gravitational constant, multiplied by m. Now this m over here is mass of the satellite. Okay, divided by ds squared. Okay, Newton gravitational force law. So this force over here is what makes it it's the cause for the centripetal force, which is given by m of the satellite multiplied by omega of the satellite squared multiplied by r. Which is r now? It is the distance to the satellite. Okay, so we will have that omega squared is g big M divided by the distance to the satellite cubed, but omega is 2 pi divided by t square root of g big M divided by ds cubed. Okay, and then we will end up getting that this period of the satellite is equal to 2 pi distance to the satellite cubed divided by g, which is the gravitational constant, mass of the earth. Now the period of the satellite, a geostationary satellite, is what? Is 1 day. 1 day. Okay, so now we have these two formulas over here. This is with and the only things we don't know in these formulas are what? Are the relationship that he wants from us. He wants from us what? The relationship from the distance to the moon and the distance to the satellite. Okay, so let's use here, this is formula 1 and this is 2. Okay, let's divide them both. Okay, so let's get the bigger picture over here. So dividing 1 by 2, okay, what we'll get, 27 divided by 1 is equal to 2 pi square root of dm cubed divided by g big M. Now remember, this m doesn't exist. This is just so that we can remember that this is the diameter to the moon. Okay, 2 pi divided by distance to the satellite cube divided by gm. Okay, so the gm will cut with the gm over here, square root of gm and square root of gm, this 2 pi, this 2 pi, and here we'll have that 27 is equal to square root of d to the moon cubed divided by d to the satellite cubed. Okay, so we will get over here that distance to the moon divided by distance to the satellite, okay, is equal to 27. Now here we had a square root, so we will need to give it a, we put it squared over here and here squared. Okay, so squared, and here we will have cubed, right? So we will need to take this, the cubic square, okay, to the 1/3. Okay, the cubic root of 27 is 3. 3 squared is 9. So dm divided by ds is equal to 9. Okay, and then we will get that the distance of the moon of the satellite is equal to 1 divided by 9 the distance of the moon. And here you, if you're maybe like in the exam you end up not understanding the question, you need to pay attention over here. This is the answer. Okay, it's 1 divided by 9. Where is the here? So you need to pay attention that over here he is telling you the multiple of the distance between the Earth to the moon is, so from Earth to the moon, multiple from Earth to the moon is equal to from Earth to the geostationary. So this is the answer. Okay, so this ends our exam, our question, but I just wanted to do something cool over here. Let's try now. This is only extra. Okay, so if you only wanted the question, this is okay over here. Okay, so just so that we maybe play a bit, maybe you're studying a lot, so we can see few things like here. What if you can see? Let me see if you can see it. Yes, over here in this part over here, what I'm trying to do is a circle. So the equation for a circle, right, x squared plus y squared is equal to the radius squared. Okay, so a bit of revising mathematics in this video too. So this x squared plus y squared gives you all the point that when you take the Pythagorean you get what? 1. So the distance between here and here, here and here, also always 1. Okay, so what do we want to do over here with this one? Well, first let me put this so it can be like this, because this will be our orbital for the moon. Okay, the orbital for our moon. Let's put our moon. How can we symbolize the moon? Because we want it to rotate over here, right? So it is a point in that it's x. When we want to make a point, we make it x and y's, right? So for example, if you want to put a point maybe over here, its x is 0.5 and the y is 1, so you get point over here. But I want this point to move like with an angle, so this part over here is cosine, and I will call it cosine of a. Okay, just cosine of a. Why? Because a will keep on moving, you will see how. And sine of a, so this is my x. Over here is my, this cosine of a represent my x, and this sine of a represent my y direction, because y is over here and the cosine is over here. Okay, so here we let me just put it from 0 to 2 pi. Okay, because it's a circle, right? This is a is my angle, is like theta. Okay, so now we can have it circling over here. Let me just change the speed. Let's put it very slow like this. Okay, so this can represent our moon. Okay, so now what do we need to do? We need to do for the satellite, but the thing is you can just call the satellite again xb and sine b, because what will happen is that you will just have another point over here, but I want it to be closer, right? Now here comes the thing, how much closer it is. Well, the relationship between it is like, if this is 1, if the radius of our from the earth to the moon is 1, so how much is the let me go back to the sheet paper over here. Can you see it? Yes. If this is 1, like I assumed like in our drawing that this is 1. Okay, if this is 1, so our distance to the from the satellite is 1.9. Okay, 1 divided by 1.9. Okay, so let's go back to the think you can see the drawing now. So what I need to put over here is the radius, okay, which is 1 divided by 9. 1 divided by 9. And put it from 0 to 2 pi. And let me put it like this. Okay, let's put the orbital for our satellite. Okay, so it will be x squared plus y squared equals to what? To the radius squared, right? But our radius is 1 divided by 9 squared. Okay, let's put this over here with dots, maybe. Yes. And let's call this satellite. Okay, so here we can see the satellite moving. Now I think that's it. If you want to see it, let's 1 second. Here, it should because I even put the speed over here. I think the speeds that I put it have a good relation, so that when this make 27 loops, this should make 1. Okay, so let's just take this off, and here we have our moon. There are no I didn't let's put the earth over here, 0 and 0. Let's call it earth, green one. Isn't there any green? Okay, this will do it. So earth. So here you go. Very nice, right? Very nice. That's it for today.